Okay, so I did a version of the apple or the potato lab using baby carrots, and here's my data right here. You can see I put it in this different molarities of sucrose solution, my ending mass, my starting mass. So the first thing I need to do is calculate percent change. So percent change, my formula for percent change is my, let's see, my ending mass. So I'm going to click on my ending mass minus my starting mass. I'm going to divide that by my starting mass. Okay, so this, my baby carrot put in the pure water got 19.9% bigger. I can just highlight this so I have the little black plus in the corner, drag it down, ta-da. And then to just turn it into a percent, I can just hit the percent button. Okay, so there's my percent change of my carrots because they all start out with different masses. So I want to use percent change to standardize that, right? So I'm comparing them all like carrots to carrots, comparing them all as though they were the same size. Okay, and the next thing I need to do is to graph this data because I need to find the 0 point here because that is the point at which my carrot's in an isotonic solution. So I'm going to grab this data, write this, I'm going to control, I'm going to grab this data right here. And you know what? Excel's gotten really good with their suggested graphs. So I'm going to go to Insert, Recommended Charts. I don't want a bar graph. I want the line graph. Okay, and I'm going to click OK. Okay, so on my x-axis is the molarity of my sucrose solution. So I'm going to add my axes titles just to keep track of that. Click on there. Okay, and I'm going to rename this molarity of sucrose solution. And then on my y-axis, that is my percent change. Okay, and I think it's dumb that this goes up to 1.2, and it's just one of those things that kind of bothers me. So I'm also going to edit my axis and make my maximum 1. Just a personal thing. It's not like super important or anything. Okay. Okay. Did it work? Okay, it worked. Okay. So I can see on my graph that my percent change of my carrot, right, had a positive 20% change in 0 molar sucrose. It had a negative 30% change in 1 molar sucrose. And I want to know, where does it have a 0% change? Because when there's a 0% change, that tells me that the water potential inside my carrot was the same as the water potential outside my carrot. And so I can find the water potential of the solution and then use that to find the water potential of my carrot. So this graph doesn't give me quite enough detail. I'm going to go back to that axis. I'm going to click on my axis. I want to make my major be 0.05. How's that look? Ooh, okay. Well, that could, it's kind of better. I think that was a little too much detail. I'm going to have my major be 0.1. I could add a trend line. I don't know if my data is quite clean enough for a trend line, but I can kind of eyeball it and see it's like between 0.3 and 0.4, probably right about 0.35. And if it makes sense to you, just be like, it's about 0.35. That's close enough. That's okay too. If you're trying to be a little bit extra, you can go back up to the plus. Sometimes it disappears. If you wiggle your graph, it comes back. Plus, I'm going to add a trend line. I'm going to click over here on the carrot on the side, not my baby carrot, and I'm going to tell it, wait, I ran out of space. Okay. Plus, trend line, more options, and I want to, oh, my picture's getting in the way. Okay, move it over there. I'm going to display, where's the one where it lets me display formula on chart? There it is, display equation on chart. Okay. Okay, I don't like that equation. Okay, so I'm just going to go with this 0.35 idea since my trend line isn't quite aligned with with where it crosses the x-axis, I'm just going to go with my idea of 0.35. Okay, so this tells me that, listen careful here, here's the confusing part. My baby carrot would have 0% change when I put it in a sucrose solution with a concentration of 0.35 molar sucrose. So I'm going to use that information to find the water potential of the carrot. But the first thing I need to know is the water potential of the solution. And I know my equation is psi equals negative ICRT. So I'm going to type in equals negative. I is 1 because I'm using sucrose and it doesn't ionize. It's just what it is. C is that 0.35 molar. I can't put units in my equation, otherwise Excel's going to get confused. So I'm going to leave those off. C. R is 0.0831 because it always is. That's just what it means to be R. And then my temperature, my classroom's always warm, so 273 for Kelvin plus, let's say 23 degrees Celsius. Okay, so this tells me that when my baby carrot is in a solution with a concentration of 0.35 molar, which calculates into a solute potential of negative 0.86, that it is isotonic. Now, this is the solute potential, right? This is negative by CRT. And I know, since it's an open beaker, that for the solution, its water potential is equal to its solute potential. So I know its water potential is the same as its solute potential, because pressure potential is 0 because it's in an open container, right? We didn't do this like inside little syringes with a bunch of pressure on them, right? Okay, so I have the solute potential of my solution and therefore the water potential of my solution. And I put my baby carrot in there. Now, carrots are plants. They do have pressure potential, but I don't know what it is. I don't know what the solute potential is either. All I know is that the water potential of my baby carrot is the same as the water potential of the solution in the beaker at that isotonic point, at 0.35 molar. So I can say that my water potential of my carrot is negative 8.6. I can't tell what the pressure potential or the solute potential is because I have two unknowns, but I know it's water potential, and that's how you find the water potential of your fruit or vegetable. And I hope that helps.